welcome everybody to first of two Intro to R workshops. My name is Shui, for those of you who don't know me. I am part of the data science core at SEATRAC, and today, hopefully, I will try to be your guide and hopefully show you some basics of navigating in R. We're gonna just start from the very basics, give an introduction of what the different parts of RStudio look like. We'll do a little bit of working with the different data types with R. We'll talk about how to import a spreadsheet from Excel, and we'll also talk a little bit about packages and getting additional help, right? Hopefully there will be plenty of time for questions throughout, so don't hesitate to raise your hand and interrupt me if I'm going too fast, too slow, or if you have questions. I think that we've got two experts in programming monitoring the chat here. So for those of you who are joining online, please also type in questions in the chat and we will address them as we go along. Hopefully you guys have already received an email from me with a link to this website. This contains all of the materials from today's workshop, which is the R Basics one, as well as the workshop on February 6th, which we'll be building on top of this to share a little bit more sophisticated data wrangling and the material that I'm going to cover for today's session can be hyperlinked. You just click on this tutorial link and it'll go to the session 1 materials. I'm going to roughly go through this content. Feel free to follow along. I think that the best workflow is for you to open up your own copy of R in RStudio and to type along as we go along. And then what we'll need as part of our demonstration is this heart disease CSV file. I think I sent that as an attachment to all of you as well via email, but if you aren't able to access that attachment, you can just right-click on this link here and do a save link as, and then the CSV file in the directory that you want to work in. Okay, any questions? All right, well, let's go ahead and get started. So I'm going to flip to R and RStudio to give you a base sense of what the RStudio console looks like. I think that oftentimes R and RStudio kind of go hand in hand these days because RStudio gives a really nice visual layout on and enhances the user experience of working with R. When you first open RStudio, you might see either 3 or 4 windows pop up in your field of view. There's this window on the left, which is what's called the console. This is where you directly interact with the R environment. You can type in commands here and it will operate and on those commands and give back whatever output you tell it. Over here is an environment, which is just a fancy name for a bookmarking window that keeps track of all of the variables that you will generate through your R session. This environment is by default kind of specific to each individual session. So if you close out of RStudio and come back in, it'll by default come up blank again. There are ways to save your environment if you want to sort of come back and continue on with the session, and we can talk a little bit about that later. And as you go along, there's another tab here that's called History, which just gives you a history of all of the different commands that you have typed in, not just in your current session, but in previous sessions as well. Down here is the view of what folders and files are in the current directory that that R is seeing. By default, it'll just be whatever your like default user directory is, but you can always navigate to a different directory. If you've set up your own little personal working folder for this RStudio session, then you can go to session, you can go to set working directory, you can pick choose directory. Uh-oh, I'm gonna have to do this. I'm gonna navigate to here because that's where I've put my stuff. Right. And then once you navigate to your new directory, you can see the contents of that new directory down here in the files. And then the last window up here, which some of you may already have, some of you may not have, is a window for your R script. So the differences between the window down here and the window up here is that the console is where you directly interface with R, but every time you open up R, it's a new console. It doesn't retain memory by default of any commands that you've executed in R before. But up here, this is your ability, this is where you can save commands and code that you've written for future reference. You can, if you don't have this visible, like you have this little toolbar up here, and you can create a new R script, right? And then you can save this R script. And you can call it something like R intro scripts. And that will be saved onto your computer so that anytime you want to come back to reference your the commands that you've written, you can refer back to it again. You can write commands down here, and it'll operate directly. You can write commands up here, and it will not operate on them directly. But if you click on this run button, then you'll see that it kind of automatically tells R to take the line that you had were just on and put it in the console and execute. Does that make sense? Okay. That might have been a little bit confusing because it was the exact same command. I will do a different command and run it again so that you can see that a new command has been ported into the console and executed, and the result comes up. Okay. I think another good rule of thumb about this scripting, like because this is your way of keeping notes of the commands that you've written, it's good to write additional notes for yourself in addition to just the commands that R will read. What we can do in order to do that is to write comments. Comments are lines in the R script that the computer will ignore. What you want to do in order to set up comments is you start the line with the pound sign, and then you can write your notes. So adding 1 + 3, for example. And if you run this, then you see that R automatically knows that it's gonna execute the line of code that's not commented, and it will ignore basically the line that is commented. The other nice thing about RStudio is that it automatically color codes comments with this green color, so that you can keep track of what are comments and notes for yourself, and what are commands that R is actually going to try to read and understand and process, right? Okay. In showing you this kind of stuff, I have implicitly also introduced the concept of R as a fancy calculator, right? Like you can use R to do all sorts of arithmetic operations, like addition, multiplication, subtraction, division, powers, all of that jazz. And R will know how to do that. When you put in a command, R will chug on it, and it will spit out the output in the black font down here, as opposed to the blue font, which is the commands that you put in. By default, when you're just writing these operations, R is not going to store the output of that information. You see that the environment is still empty. If, for example, you wanted to store the answer of this calculation into a variable so that you can refer to it in the future, then you want to be able to write the operation, but assign the output to a specific variable. So let's say addition variable equals 1 plus 3. And if I run that, you see now that a variable has popped up in our environment that is equal to the answer of 1 plus 3. So if you wanted to refer to the answer addition variable, you can just type in addition variable. And I'm going to start typing, and RStudio is already prompting me that there's a variable there called addition var. And it might save you some typing to be able to just press tab, and it will tab complete the name of the full variable. And if you just click and run that specific command, it will output the answer addition variable that you have previously stored in a previous command. This is useful when you might prepare complex operations that span more than one line. You might want to store the answer and keep use that for other operations, and it'll keep the answer for you over time. The one thing about R and other programming languages is that it's really easy to overwrite the contents of variables. So for example, if I changed addition variable command here to 2 plus 3, for example, and run that, and if I rerun addition variable now is 5, right? Like R does not prompt you to say like, are you sure you want to overwrite this variable? It will just do it for you. So don't be afraid to create lots of variables if you want to keep the information stored in each of them separately. But on the other hand, sometimes you don't need to know addition variable for more than one step, in which case you can just overwrite it pretty straightforwardly. A few other notes. The way that you want to pick the names of variables, it needs to start with a letter, either capital or lowercase, and it can also contain numbers in the name. It just can't be the first letter. You can also have underscores if you wanted to. So for example, addition variable 2 plus 3. If I did this, for example, that also successfully stores in R as a variable name. But you don't want to use hyphens because R thinks of that as subtraction. And you don't want to start a variable name with a number as a rule of thumb. I think that if you end up writing a set of code that has lots of different variable names, it's often good practice to try to make your variable names informative so that future you can have a clue as to what types of operations you're trying to get R to do, instead of like just doing A, B, Z, which can be ambiguous. Here I've written addition variable, 2 plus 3, which is basically cluing in future me that I wanted to have the output of this variable be storing the operation of adding 2 plus 3, right? Any questions about that? All right. So I think I belabored numbers a lot. So let's move on to the other data types in R that may be less intuitive for you guys. Another really useful data type in R is a logical or a Boolean. So there are two types. It's true or false. It just tells you whether a logical test is true or false. So for example, we can test whether 3 is less than 5, right? And if we run this, 3 is indeed less than 5. But if we were to sort of run the opposite, 3 is not greater than 5 because 3 is less than 5. Those are the two logical types. You can stitch multiple logical queries together using and or functions. So for example, let's test if 3 is greater than 5. Or 3 is less than 5. I'm gonna put these parentheses to keep track, both for myself and for R, like which tests we're doing. Testing or. The or operator is this vertical line here. And this is true because it has to be one or the other, right? But if we wanted to test and, the and operator is the ampersand. And both parts have to be true in order for the combined output to be true. And in this case, because only one of the two statements is true, the result is false overall. And just with numbers, you can also store these logical operations in variables. So if we were to do something like this, logical test is now a variable that stores the output of this evaluation is 3 greater than 5 and 3 less than 5, false. And if we were to try to call on logical test again in the future, right, logical test, the variable will store the outcome of that evaluation that we did before. Okay. This third type of data that I'd like to talk about are strings. Because it's all very well and good to be able to work with numbers. We as scientists love working with numbers, but being able to work with characters and groups of characters is also useful because, you know, sometimes you want to be working with gene names. Sometimes you want to be working with patient characteristics that are best described as a word rather than a number, right? And R enables you to work with those kinds of things using the string data type. So in order to create a variable that has string in it, let's create a variable called string var. We can write either double quotes or single quotes, and then put some words, some letters in on this. You can see that the variable string var now stores the content hello, and hello is a string data type. Now, just as with numbers, you can perform logical tests on string variables. So you can test string equality. I'm gonna do really confusing things, but this double equals is asking R to evaluate whether the thing on the left is equal to the thing on the right. Hopefully this will work. And you can see that test string equality says true because this is identical to this. The string equality evaluation is case sensitive. So hello with lowercase is not the same thing as hello with uppercase. Right? Furthermore, if you ever have like misspellings, that is definitely not the same. If for whatever reason you wanted to test whether something is not equal to each other rather than equal to each other, I believe you can do, no, R is this, I think. Nope, R is this. Sorry, it's always something else, and it's different in different languages. In our testing or not equality is this, right? Any questions so far about strings, numbers, logicals? I think that the concept of doing logical tests can be super useful when combined later on with spreadsheets, because oftentimes you want to operate on only a subset of your spreadsheet of interest, right? And rather than telling R explicitly which row numbers and which column numbers to work on, you can design these logical tests to tell R, I want to operate only and subset the spreadsheet only based off of the criteria X, Y, and Z. And you can build in these logical tests to get R to subset down the rows and the columns that fulfill those criteria, rather than having to manually find out those rows and columns yourselves. So, yeah, logical, being able to formulate logical tests is a useful thing that can be built up into like pretty complicated and pretty useful commands. Okay, so this is all very well and good. We've been spending some time working on individual data types, but like really as biologists, we're often working with multiple measurements at the same time, right? We're working with spreadsheets with not just like a single row or a single column. We're working with two-dimensional spreadsheets with columns and rows, right? And R is able to store pieces of information in groups at a time through objects such as lists and data frames. I'm going to start by talking about lists, which are objects in R that store one-dimensional groups of information. So just one, just like the equivalent of one row or the equivalent of one column, because the concept of being able to pull out subsets from a group of an object that has a group of things is often non-intuitive, and it's easier to sort of talk about subsetting with one dimension at a time first. But we'll go from there. So lists, let's create a list. We're going to start with a really easy list. In order to create a list of numbers, the command for that in R is C. C kind of combines whatever inputs you want into a list. So store that. If you call up the contents of that, num list now contains not just a single number, but a group of numbers all strung together in the order 1, 2, 3, 4. What's cool is that you can perform logical operations on this list variable, and by default what it does is it will evaluate each element in this list independently, and it'll give you an answer for each element. So for example, num list greater than 3 is asking R to test like which ones of these elements are greater than 3. We do that. You see the output is false, 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 true, because only the last element in num list is greater than 3, because it's 4. The other elements are all either 3 or less, right? And you can imagine, as an extension to this, if you were to input a spreadsheet and you evaluated, okay, how many, like which elements in this spreadsheet have like, you know, a blood pressure greater than 100, for example, you can construct a command similar to this to say like column greater than 100. It'll output falses for all of the rows that are less than 100 and trues for all of the rows that have blood pressure greater than 100. And you can then use that information to subset only the rows that you care about that are like greater than 100, for example. Right? I want to just briefly share a shortcut way of creating a list that is a consecutive set of numbers. In R, you can do this using a colon operator. So if you do this, and then you say numRange, you can see that R automatically builds a list that starts at 1 and ends at 4 and goes consecutively from 1, 2, 3, 4. It knows to fill it in. What's nice is that lists are not only just for numbers, you can also create lists of strings. And you'll notice that I am using single quotes to define the strings here, just because I'm being lazy. And that R is also smart enough to detect that these words correspond to colors, and it's automatically coloring that. How cool is that? So if we save this word list, you can now ask R to evaluate whether a specific string is in this list of strings. That's right. So like if I were to ask, is red in word list? Whereas if I were to say like, hello in word list, it's going to be false. And again, if it's like, it's also case sensitive. So red with a capital R is not going to cut it. Right. Any questions? So there's a fair amount that you can do with base R, not just the things that we've talked about, but the true power of R is taking advantage of functions and of operations and of other commands that other users have developed. And a lot of these functions are contained in our packages that you have to install and load into R. We are going to be using, particularly in the second lecture, a collection of packages called the tidyverse. Whenever you're installing a package, you can do that within the R environment using the command install.packages. That is, I would say, 85% true for bioinformatics stuff. There are some bioinformatic packages that live on a site called Bioconductor, and the installation is different. But for packages that don't live on Bioconductor, install.packages will work. As an example, I'm going to show you how to install the package called tidyverse. So install.packages, and then tidyverse, which is the name of the package, input as a string in single or double quotes. So I've already installed tidyverse, but for those of you who have not previously installed tidyverse, it's probably gonna list a whole bunch of things that should hopefully say, like, this package has been successfully installed. You only need to run install.packages once. Once it's installed once, once you close R and open up R again, you can just load up the package to use it in future times. So how do you load a package? You load a package using the command library. And in this case, you don't need to put the name of the package in quotes. It's just, you put it in as if it were a variable name. And in this case, because tidyverse is actually a group of packages, it kind of shows you a check mark to confirm whether all of the associated tidyverse packages were successfully loaded or not. I think that sometimes you'll see conflicts. This means that there are some commands in some of these packages that have an ambiguous function name relative to other packages that are pre-installed, and you can resolve conflicts by using the syntax, like the package name, : function name, to delineate which version of the function that you would want. I think for basically all of what we're going to be talking about today. And on Tuesday, that's not going to be super relevant, but it's good to know. All right. So the reason why we wanted to install Tidyverse is because Tidyverse is a really nice way to keep track of data that you import into R through spreadsheets. And so now I'm going to try and share a command for how to install, how to load a data set from an input spreadsheet. So what you want to do is you want to make sure that R is seeing the spreadsheet that you want to input in the files folder. It needs to be in the same directory where R is looking, I guess. If you don't have that there, you want to go to Session, Set Working Directory, choose the directory that matches where that CSV file is. Okay, I'm already there, so I'm not going to actually change anything. But from there, once you've navigated to the right directory, what you want to do is you want to use the command read underscore CSV, and then you want to type in the name of the spreadsheet. And I'm going to run this first in a way that you wouldn't normally run it, just to show you the default output. You can see it, that at the end, R will give you an output that summarizes the data that it pulled in from the CSV file. But the reason why I mentioned that it's not how you would normally want to do it is because you see that in the environment, what we read in doesn't exist yet, and that's because we didn't store the output of read CSV into a new variable. So you want to make sure that when you're importing data that you save it as a variable. And if you do that, then a new type of environmental variable comes up, which is in data. And if you double click on this, R very nicely it gives you this nice spreadsheet visualization of the top few rows and columns of your spreadsheet that you just imported. And you can just double check whether that spreadsheet looks correct and matches what it shows up in Excel, for example. If this looks wrong, then you can always go back and change the command that you used for importing and make adjustments there. How do you make adjustments? Well, you can always come here and ask for help in the help button. Put in the name of the command, and it gives you a lot of information about what the different inputs and outputs are. I think I'm going to come back to this, but we'll also talk a little bit about how you can look for help on the internet as well. But for now, we're going to do a little bit of playing with our data variable, which contains all of the information that we imported from our CSV file. You can ask R to give some summaries of the data variable. You can say dim data, which gives you the number of rows and columns. The rows always comes first, and the columns always come second. If you cared specifically about just the rows or just the columns, then n row gives you the number of rows, and n col gives you the number of columns. Okay. I think we talked about the view of the data that you can do just by clicking on this. And you can see that RStudio sort of copies this command view data, which is the actual command that brings up this spreadsheet view. And then STR data gives you a summary of the top few rows and columns of this data frame, as well as the specific column names, which we'll get to in a little bit. Okay, so this is all very well and good, but oftentimes when you want to import data into R, you want to be able to extract out specific subsets of that spreadsheet to perform mathematical operations or to perform visualizations, right? So being able to extract specific subsets is super critical. The syntax for doing that in R is with bracket notation. So we'll start with super simple. This syntax bracket 1, 2, 1 comma 2 is telling R to spit out the value in the first row and the second column, which we can double check in our view. So the first row, second column is number 51, and 51 gets spit out. Yes.
Sorry, I'm a little bit behind, so I think I can take that in.
Oh, okay. Yes, absolutely. So you're stuck on importing the data? Okay. So two important things is you want to make sure that this input CSV file is in the directory that is listed here. And you can double check whether that's true in the window down here. You can see that I'm in the same directory here. And I see the CSV file. And then from there, the command is read CSV, and then the name of the file. And if you need to change your directory, you want to go session, set working directory, choose directory. And then you just want to navigate to whichever directory has your CSV file. There are probably additional complexities that I'm not really going into right now. But okay. Is that working? Okay. The other complication is installing tidyverse. You need to do install.packages tidyverse. You need to load tidyverse with the library command. And whenever you are working with a package that is not in base R, you need to do the loading that package with the library command every single time you initiate R. So that is something that you do. Yeah.
With that, just the install packages command, when it says our tools is required, our tools is required to build our packages. So should I be downloading our tools first?
Try writing install.packages are tools.
Okay. And the other one with the same install.packages, I just command I'm getting try removing the lock on a directory, which I don't remember pressing a lock on any directory.
Are you using your own personal computer?
That our tools warning is okay. I got that too, and I can still manage it.
Installing packages is always the most challenging thing. I think because there are some challenges, I'm going to show you an alternative way of loading a spreadsheet into R. Very closely related.
Anything.
There's a command called read.csv instead of read_csv that you can use. And it can also import it into R. What's the difference? There's a lot of difference under the hood. There's a way, there's the data type that the data2 variable gets stored in is different from the tidyverse version. And so some of the functionality associated with the data variable will not be available in the data2 version. But if you are having trouble with the tidyverse library, a lot of what we're going to talk about next can be done with data2. So for example, data2 also allows you to pull out value 51 by pulling out, by subsetting the first row and second column. And you can also do dim data2. There are a lot of similarities. I do not believe that you can do str data2. Oh, you can. How about that? You can do string data2. I'm also going to say that while we've been editing this R script file, the text here has a star next to it, and the text is red. That means that you've got unsaved things in R script. If you click the save button, that just goes away, and that shows that you everything that you've added has been saved. Okay. Should we take a little bit more time with the install situation, or should we try to move on with the alternative loading of the data frame? Okay. Are you able to do read.csv into data2?
We'll try.
Okay. Let's try to get there.
Yeah, installing tidyverse seems to be crashing the computer.
I'm sorry.
So
Let's do read.csv. Because I think for almost everything, probably everything, we can just do it with the data frame that you get from read.csv. No need to apologize. I think installations are the most painful thing with R. Okay.
yeah, you can definitely continue.
All right.
But
so the general convention of subsetting data frames, either data frames from read.csv or data frames from the read underscore CSV of the tidyverse, is this bracket notation where you're telling R to pull out either an individual row or a range of rows, and either an individual column or a range of columns. What's nice about the subsetting schema is that there's a lot of flexibility for how to subset. You can either do individual elements like this. You can do oops. You can do a list of elements. And so this is asking R to pull out the first row, the third row, and the fifth row in the second column. And you can, oops. You can double check that, right? First row, third row, fifth row, right? You can use that range notation from before. And this is saying, I want to pull out the first 4 rows from data in the second column. Why the second column? Just kind of arbitrary. Yeah. Ah, great question. So you can come here into the environment tab and you can click on the variable that you want to highlight. And then it should pop up a separate tab. I like to do this just to sanity check myself, although it's certainly not essential. What's also cool is if, for example, you wanted to create a logical, we can set that up. But in order to do that, I'm gonna show you a few other things first. So if you wanted to like pull out an entire column, for example, entire call to, you can do data and just leave that first element blank before the comma. And you can see that that just pulls out everything in the age column, right? And what's also notable is that age is the name of a column. And so you could potentially also do you can call it by age. And you can do that in a couple of ways. You can use this $sign notation. You can do in the bracket notation and referred to age with a string. You can see. Why is the entire age column not up here? There's a subtlety there that I don't really want to talk about. The data $age stores the contents of the data frame in the variable, essentially as a list. So it like looks like a num list, whereas doing this bracket notation changes it into like basically a data frame that has a single column. For the majority of what you're going to be using, it doesn't really matter. But there are, I think, some use cases where specific packages might expect one type of input versus another, like a list versus a data frame. But all of this is really useful because then you can do something like which rows of young rows right? You can ask R to sort of pick out which rows have values that's less than 80. And I guess almost all of them are young. And if you wanted to subset on that, you can do data, young rows, and you can do it either just by age, right? You can do data not young rows. Well, yeah, only the one that's like not less than 80. And you can also do it for the entire data frame. So like looking across columns, not just the age column. So you can say like, okay, I want to figure out which patient is not younger than 80, and I want all of their stats. This way you can build in this logical to pick out which row you want, but then but you don't define which column you care about. And the output pulls out everything. I'm going to just show you really quickly what that looks like in the non-tidyverse version. Right, it's really similar. It gives you the same stats, just the output looks slightly different. But this patient is female, blood pressure 149, cholesterol 161, et cetera, et cetera. So what I'm trying to say is that you can start building in kind of complicated ways of subsetting specific rows of interest and specific columns of interest based specifically on the criteria of specific patient parameters that you care about, right? In this specific case, I've built up this logical query based off of the age that is the contents of the age column. And then I use that to subset out and pull out only the rows of the age criteria that I cared about. And I was able to do that without knowing which rows that patient came from. Does that make sense? Questions about that? Okay. So being able to just pull out data is all very well and good, but a lot of the times when you're working in R, you actually want to be able to do some calculation or some analysis with it, right? And I think R is particularly powerful for applying statistical tools to data sets. So I'm going to just show you one example of that with a simple t-test. I think it's beyond the scope of this class for me to explain what a t-test is, but I think that the nutshell is that it is a statistical test that sort of evaluates whether two distributions are equivalent or not, right? The syntax for a t-test in R is t.test. And I'm going to just pull up the help function here so that you guys have this as a reference. But basically, you want to list what's the first set of samples that you want to compare against the second set, that with a comma in between the two arguments. And so let's say that we want to do data, and I'm gonna check data. I'm gonna use this $sign notation, and I want to see heart disease status, right? And I'm gonna sort of say that I want to see for only the patients where the heart disease status is true, I want to look at the BMI. And then I'm going to say, I'm going to just copy and paste that command again. And I'm going to say no. And this command will t-test whether BMI is different for patients with versus without heart disease. Oops. The t-test will output a series of statistics that summarize what the value is, including the p-value. And it's saying that in this case, there isn't a statistically significant difference between the BMI of patients with heart disease and patients without. To just break it down a little bit more, I'm gonna show you what this actually looks like. So first of all, I'm gonna subset just on the patients of heart disease status. I'm gonna say, and I'll store that in a variable so that we can view it carefully. Heart disease, yes. So there are 24 of these patients, and you can double check that all of these guys have yes in the heart disease status, right? And these are all of their other parameters. And if we sort of further subset that to heart disease, yes, BMI, that is pulling out specifically the BMI column from heart disease, yes. You can just double check, squint at it, that it is in fact just that subset. Copy this back in the script. And similarly, right, you can create a heart disease no. And a heart disease no BMI. These all have heart disease no, and they have, these are all of the columns, right? And then heart disease no BMI matches the contents here, but just for the BMI column. And if I were to do the t-test again on these variables that I stored, it would be identical. Right, it was the same p-value as above. So I think that, like, just in terms of how you would construct this code yourself, it's completely up to you whether you want to create these variables for yourself and use that to keep track of like your workflow, or whether you want to do what I did above, which is do everything in a single line of code with the subsetting kind of embedded inside. Like R is flexible in how it allows you to represent the data input. And whatever makes more sense for your brain is what you should do. So I showed you how you can use the help tab here to pull up that help function. There are other ways of asking for help in R as well. Within the console, you can type in the question mark, the name of the function, and it also basically pulls up the help page here. If you don't find the documentation here particularly helpful, then sometimes it might also be useful to just look at some use cases, example use cases that R has by default. And you can do that using the example function. And so there are all sorts of specific examples worked out. Any questions about that? Any questions about anything at all that I've talked about today? Okay, I think that because we still have a little bit of time, I'm going to show you the bonus example. just to do one other fancy thing. Because for Hack Day, we're going to be working with clinical data, and a common analysis associated with clinical data is to use linear regression to find associations between groups of parameters. And in R, the standard linear regression function is super easy. It's called LM, which stands for linear model. And so I'm going to just show you how you can set up a linear model in R. Linear model. Okay, so with linear models, there's sort of an independent variable and a dependent variable, right? And you can have basically multiple dependent variables that you're evaluating for, like, to what extent is there an association between your independent and your dependent variable. And so we need to define each of these different pieces. In my example, I'm going to ask whether the BMI parameter has any association with other patient criteria like gender or smoking or exercise. So I think, as with the t-test, you can either embed everything directly, or you can define each of the parameters as separate variables and link them together. I think for clarity, what I'm going to do is to define separate variables for each of them, and then build those variables together in the LM function. So I'm going to start by setting a variable called independent variable that just has the values in BMI across all of the patients. And then I'm going to do gender. And I'm going to do something fancy here. I'm going to say as factor data.gender. What does as factor mean? Well, let me show you. So by default, right, gender is a string variable that either has male or female, but R doesn't recognize strings as particular categories that you can perform mathematical operations on. In order to get under R to understand that these are two categories that I want to use as like a mathematical label in regression calculations, you want to convert the string into a factor. And so in this case, what it's saying is the gender, we've defined male as one category and female as another category. Those essentially implicitly have numbers 0 and 1 associated with them. And you can then perform a regression on 0 and 1 rather than like an arbitrary string. We're going to do the same thing for a few other variables, just for funsies. Right. And each of these is going to be a factor that defines whether the patient smokes, whether the like what kind of exercise level that the patients have. And then we can pop everything together into our linear model. LM, it's the linear model. Dip. There. And the squiggle is saying we're associating our independent variable with our dependent variables. Okay. Now there's nothing stored yet because we put the output of the linear model in this variable, but we can tell R to spit out a summary of that linear model with the summary function. And the summary gives you a sense for what the specific linear model coefficients are and what the p-value of those coefficients mean. A significant p-value would indicate that there is a statistically significant dependency between the independent variable, which is BMI, and the dependent variables, which are smoking, exercise, or gender. And what's nice here is that because exercise had like low, medium, and high, it evaluates a dependency for each of those levels. But what's interesting, right, is that like in this case, there isn't really a dependency between BMI and any of the input dependent variables that we evaluated in our model. The only thing that's statistically significant is the intercept, which means that there's some sort of basal BMI value that comes in, but and that the BMI values in our table are non-zero basically. But there isn't a linear relationship between BMI and any of the 3 dependent variables that we evaluated in our model. These parameters down here, the residual standard error, R squared, and F statistic, gives a sense for what the overall fit of the linear model is. This adjusted R squared, almost 0. That suggests that there's no trend between any of the dependent variables and our independent variables. And let's see what happens when we do this. Right, this kind of plots fitted values versus residuals. That just means that there's like a lot of variation in the BMI values across patients that are not explained by the dependent variables that we looked at, gender, smoking, or exercise. So it's kind of cool that there are a lot of default outputs in the plotting that are just knows to be able to plot from the output of the linear model. And I think for more information on that, this is probably a good place to go. and examples. Also gives you a lot of great information. With other specific examples. Does anyone have any questions? All right. Well, if there's no other questions about anything from anyone, I think this is probably a good time to probably close. We've only got 4 minutes left in our session. Thanks very much for following along. I appreciate your attention and for coming today. And we'll see you February 5th for more data manipulation. Did you guys manage to get everything to work? Do you have any questions? If this was
No, I think I need to just go back. And it's like telling me that I didn't find one of the variables, like I might have did wrong and all that. So. When I took like an intro course like years ago to R, I kept using carrot a lot. So I don't know. That's the only thing I remember.
carrot.
I don't know if they were doing for